My name is Dr. Cameron Kristopher, and I'm NEWA's Chief Scientist for High Performance Computing and Data Science. In my role, I oversee NEWA's supercomputing capability, as well as our data science and our data analytics functions. The title of my talk today is How Supercomputing and Data Science Are Supercharging NEWA's Environmental Science. So NEWA, we're a Crown Research Institute here in New Zealand, and the sciences that we cover, our key three platforms, are climate and atmosphere, ocean sciences, and freshwater and estuary sciences. Almost every part of those sciences, there's a data aspect to, right? So almost everything touched by NEWA researchers has a data component. And then beyond the research side into the operations side, there's also a massive data component here at NEWA that we look after. If you look into the sciences that we do, if you look at the underlying environmental processes, there's quite a bit of information out there in the environment that we need to collect. So we're looking at climate, we're looking at cloud visibility and radiation, we're looking at river flows, we're looking at ocean temperatures and salinity, we're looking at soil moisture, water quality, air quality, we're understanding the ozone, looking at ocean bathymetry, looking at sea level, looking at snow and ice. There's a massive amount of data out there. And one of the things that we do here at NEWA is we develop ways that we can collect that data. So we have a massive infrastructure for the development of new instruments and systems and sensors in those systems that can help to better detect what's going on in our environment. We also have a huge infrastructure that actually maintains those systems, that deploys them, and ensures they're working properly, makes sure the continuous maintenance is there so that we can get the accurate information from the environment that we're seeking. And this deployment, really the coverage of New Zealand that NEWA has, and it's massive, and I'll go into that in a bit. It's quite tremendous in our ability to actually understand what's happening across multiple terrains. So, for example, this image here is taken in the Fiordlands, but we have sensors all the way down in Antarctica. We have sensors into the Pacific Rim as well. We have sensors here in places like the Waitomo Caves. So we're doing a massive amount of monitoring in New Zealand, and it's a huge data infrastructure and teams and development of instruments that supports that collection of information. If you start to look at the network that we've developed out across New Zealand to collect information, you're looking at a network that consists of over 140 automatic climate stations, 40 manual climate stations, over 250 manual rain stations, about 50 hydrometric stations, and 50 water quality sampling stations, 3 sea level rise stations on top of that, and then beyond that into the commercial operations domain, where we're supporting over 500 different stations for commercial operations in the energy sector, for example, or for regional councils, and a lot of these stations in the irrigation sector as well. We're looking at a lot of hydro stations, a lot of rainfall stations, looking at groundwater stations, and also looking at wave monitoring. So it's a massive infrastructure. All in all, we're looking about 1,000 plus major and minor stations that we're collecting data from a NEWA perspective, plus another 1,000 third-party data sources that we ingest. Now, on top of that, we also have about 8,000 historical stations that we have archived in our system. So you can imagine the scale of data here at NEWA is massive, and our ability to actually sustainably ingest that data and perform different modeling and processing and analytics tasks on that data. It's very, very important. So I talked a bit about the network that we have set up of stations, but also digging deeper into some of the tools that we have deployed that collect data for our scientific discovery and innovation. We're looking at our massive fleet of drones, aerial drones collecting information, or our underwater drones. We have ROVs underwater. We have AUVs out collecting information, about the ocean floor, bathymetric information. We also have our research vessels, which are world class in their ability to go out and perform research and collect information about our environment. So, the scale of the data here at NIWA, what we can do with that data, our ability to create insights for industry from that data is super important for the New Zealand ecosystem as a whole. So beyond collecting data, you actually then need somewhere to actually store that data. So we maintain massive national databases and collections. We maintain the quality of that information, ensuring that any information that's missing is accounted for, and that we can identify bad data that exists. And that we can infill data when appropriate. So this data is of the highest standard. We perform regular audits on that data as well to international standards. And more we're finding benefit, and this is into the data science domain. More and more we're finding the benefit of data science and actually helping to automate some of these tasks, helping to automate the uncertainty quantification in data, and helping us to better plan how we collect data going into the future. So this is one of the key benefits that we're realizing with data science. So once you actually have all of that data, the next step is actually to turn it into information that can be used to tell us about the processes, to predict what's going to happen in the environment, to help better mitigate and potentially prevent things from happening, but help operational planning even, right? So that's the next step after you actually collect the data. And then move into this kind of modeling and simulation space where we have global weather models, we have global climate models, we have catchment models that we develop, we have wave models, high resolution weather models, we have data analytics that we start to perform on that information, doing economic modeling, reaching out into wider New Zealand factors, risk modeling, tide models, ocean flow models, fishery models. We have all this information that we've collected from these sensors from the ground up that we developed. We developed these sensors. We collect the information. It comes through our massive national databases. Now we're able to start to do modeling. We start to do simulation of the environment, and now we can start to do, next level. How do we start to make sense of that information for different contexts? Now, in order to actually support this mega infrastructure of data collection and scientific discovery, NIWA hosts some of the most advanced supercomputers in the world. And I'm talking, supercomputers that can perform 2,000 trillion calculations per second. We can analyze data at exabytes of scale, at petaflops of speed. So this is really a massive infrastructure, all the way from down at the sensor level through our network, which covers a massive range of terrains in the marine space, all the way through. Now we're able to process this data and develop these complex physical and environmental simulations based on the information that we collect using these very advanced supercomputers. So it's really giving us that edge in understanding the environment, understanding the impacts, and knowing where we're going in the future. Some of the kind of key things that we're modeling on these massive supercomputers and some of the key kind of impacts which we're understanding is, for example, modeling the impacts of climate change, which is obviously huge at a global scale and of significant importance for the wider wider Earth system modeling studies. We're also forecasting weather-related hazards. We're analyzing genetic information, understanding the systems that drive our oceans, tracking New Zealand's freshwater resources, investigating New Zealand's seismic risks, and also developing and building these complex AI algorithms, which is a big part of my function here at NIWA. When we start to move into understanding the impacts of these environmental models and processes, you're looking at things like floods, you're looking at droughts, you're looking at waves and wind, which can cause damage, primary productivity, diseases, air quality, water quantity, the impacts that these have on things like transport operations, how we can develop more renewable energy sources, the fisheries quota levels, all the way into the financial sector, into the insurance sectors, into the health sectors in New Zealand. It's a massive amount of that we're doing in terms of how we actually make sense of this information, how we support decisions for wider industry here in New Zealand and globally. And it's really, it really speaks to our ability to have this massive data infrastructure from the sensing capability all the way through our ability to run massive simulations and calculations on this data using our supercomputing capability. So it's really a key advantage that we have here for New Zealand. Our connectivity and the scale at which we're able to compute here is massive. So in terms of our growth and what's happening in the New Zealand environmental space and how that interacts with the wider economic and social consequences, we really are on the cutting edge. Excellent. Thank you for your time, and feel free to ask further questions.